Have you ever stopped to think about the air you're breathing or the water flowing from a tap? Well, there's a hidden science that governs all of it, from the weather in our atmosphere to the blood pumping through our veins. It's called fluid mechanics, and honestly, it's like an invisible force that shapes our entire world. Once you learn how to see it, you start finding it absolutely everywhere. So let me start you off with a bit of a riddle. What could a simple bottle of ketchup possibly have in common with a gigantic, powerful hydroelectric dam? I know, it sounds like a joke, but the answer actually pulls back the curtain on the fascinating and sometimes just plain weird world of fluid mechanics. So to figure that out, let's dive right into our first section, the secret life of fluids. We're going to start by exploring the core properties, the very personality traits that define how different fluids behave. Okay, first up is a big one, viscosity. The easiest way to think about this is as a fluid's stickiness. It's basically its internal friction, how much it resists flowing. You know, honey has a really high viscosity. It's super thick. It flows really slowly. Water, on the other hand, very low viscosity. It flows freely. But, and this is where things get really cool, that stickiness isn't always a constant. Most fluids we deal with, water, air, they're called Newtonian fluids. Their viscosity never changes no matter what you do to them. But then you've got the rebels, the non-Newtonian fluids. Their viscosity actually changes when you put them under stress. Ketchup is a perfect example of something that's shear thinning. It gets less sticky when you shake it or hit the bottle. That's why it stays put, and then whoosh, it all pours out at once. And then you have the opposite, shear thickening fluids, like a really dense sugar solution, which get more solid when you apply force. Two completely different personalities. So we've seen how fluids can have these wild personalities when they're moving. But what about when they're not moving at all? That brings us to our next section, the power of stillness, where we'll look at fluids at rest. Believe it or not, a fluid that's perfectly still is still exerting some incredible forces. The most famous one, of course, is the buoyant force. This is that upward push a fluid gives to any object sitting in it. It's the entire reason a massive steel ship weighing thousands of tons can just float on the ocean. The upward buoyant force from the water it displaces is actually stronger than the ship's own weight pushing down. But hey, it's not enough for a ship to just float, right? It also has to float stably without tipping over. The secret to that is a concept called metacentric height. You can basically think of it as a measure of a ship's tippiness. It all comes down to the relationship between the ship's center of gravity and its center of buoyancy. The bigger this metacentric height is, the more stable the ship is. It creates this powerful righting force that pulls it back upright every time a wave tries to tilt it. It's this brilliant, invisible bit of engineering that keeps these huge vessels from capsizing. Okay, enough of things sitting still. Let's get things moving. Time for our third section, the rhythms of flow. This is where we get into the beautiful and sometimes chaotic world of fluids in motion. So, when a fluid flows, it generally has two main modes. On one hand, you've got laminar flow. Picture polite, orderly traffic with everyone staying in their own smooth, parallel lanes. Then, on the other hand, you've got turbulent flow. Think of that as a chaotic mosh pit at a concert, swirling, unpredictable, and all mixed up. The big switch between these two is determined by something called the Reynolds number. It's basically a value that compares how much momentum the fluid has versus its own internal stickiness. Keep the Reynolds number low, and things stay calm and laminar. Crank it up, and you get turbulence. So how do we even begin to make sense of all this motion? Well, a huge piece of the puzzle comes from Bernoulli's principle. At its heart, it's really all about the conservation of energy inside a moving fluid. But the big idea, the main takeaway that you absolutely need to know is this simple trade-off. Faster flow equals lower pressure. And that simple relationship, that is the secret to flight. An airplane wing is specifically shaped so that the air traveling over the curved top has to move faster than the air moving along the flat bottom. Faster air on top means lower pressure on top. And that means the higher pressure underneath literally pushes the wing and the entire airplane upwards into the sky. Lift. It's that elegant concept that lets us fly. And that very same principle, managing pressure and flow, is totally fundamental to how we engineer things in the real world. Which brings us perfectly to Section 4, harnessing the current. This is where we see how all these ideas are really put to work. And this, my friends, brings us right back to our hydroelectric dam. A hydraulic turbine is just a masterpiece of applied fluid mechanics. It takes the immense potential energy of all that water stored up behind a dam, channels it through guide vanes to make it go really fast, and then uses that powerful jet of water to spin a runner. That simple act of converting the fluid's energy into rotational mechanical energy, that's what generates electricity for millions of us. We are literally harnessing the power of the flow. But here's a weird twist. Engineering is just full of these interesting trade-offs. To get the most power you can out of water flowing through a pipe, you'd think you'd want to get rid of all the friction, right? Well, you'd be wrong. It turns out the maximum theoretical efficiency for transmitting that power is actually achieved when a full 1/3 of the energy is lost to friction. It's this wild, counterintuitive idea and a perfect example of how engineers have to find the perfect sweet spot between all these competing forces. Okay, so this all seems incredibly complex, which brings us to our final and really important section, modeling the invisible. How do engineers actually predict and design for something as wild as fluid flow without having to build a full-scale jumbo jet or a massive dam for every single test? Well, the answer lies in something called dimensionless numbers. These are genius. Each one represents a ratio of different competing forces. So remember the Reynolds number we talked about? It compares inertia, the fluid's tendency to keep moving, against viscosity, its internal friction. By making sure these key ratios are exactly the same between a small-scale model and the full-scale prototype, engineers can accurately predict how the real thing is going to behave. It's how a test on a little model airplane in a wind tunnel can tell you exactly how a real 747 is going to perform. The mathematical magic that makes all of this possible is a mind-bending idea called Buckingham's pi theorem. To put it simply, it's a super powerful method that lets engineers take a crazy problem with dozens of complex variables, like temperature, velocity, density, size, you name it, and boil them all down to just a handful of those meaningful dimensionless numbers we just saw. It is the theory that makes all of modern fluid modeling even possible. So there you have it. From the way your ketchup pours, to the way an airplane flies, to the way we generate clean energy, the principles of fluid mechanics are absolutely everywhere. We've used this knowledge to design everything from supersonic jets to life-saving artificial hearts. And that leaves us with one final question. What is the next great challenge we can solve by understanding the secrets of the flow?